Hello and welcome to the awesome biology channel, where today I'm going to be talking about protein gel electrophoresis, which is a really cool set of techniques that use electricity to separate out different proteins in a mixture and to help identify what those proteins are. Now first I'm going to be talking about sodium dodecyl sulfate polyacrylamide gel electrophoresis, or SDS-PAGE gels, also known as denaturing gels, and then I'm going to talk about the native or non-denaturing gels. Now these gels are all about the protein, and I love proteins, so come on, let's check it out. Okay, so let's start with our sample preparation for SDS-PAGE or denaturing gels. Okay, so let's talk proteins. Here I show you three different proteins. Now remember, a protein is a chain of amino acids, and these amino acids can have bonds between them that end up giving the protein their shape, so they're folded. Now we're going to treat our proteins with heat and a detergent called sodium dodecyl sulfate, or SDS. Now the SDS will come and put a negative charge onto each of these proteins, and the heat together will help to denature or unfold these proteins. Now you'll see that the negative charges on the proteins, it's always relative to the size of the protein. That means smaller proteins will have fewer SDS charges on, larger proteins will have more SDS negative charges on there. So this means these proteins will always have the same mass to charge ratio. Now if you were to do this in a lab, you would be adding your SDS, say for example the pipette, and you'd be doing this on a heat block or a water bath. But here what we're doing is we're heating up these samples in the SDS, in their buffer, and this is going to denature and roll those proteins right on out to gather the heat in the SDS like a boss. There are some proteins that have these very strong covalent bonds called disulfide bonds or disulfide bridges. Now the heat in the SDS can go to work on the rest of the protein, but they together can't break these strong disulfide bonds. So we need a separate ingredient, and we'll use what's called a reducing agent. Some examples of reducing agents are dithiothreatol, DTT, or beta-mercaptethanol, beta-ME. So these guys specifically can go and actually break that very strong covalent disulfide bond, so that the protein then can become linear and still get coated with that regular charge, the negative charge of the SDS. Now just as a note of reference, in fact there are some proteins that are made up of multiple subunits, and that reducing agent, if those subunits are held together by disulfide bonds, the reducing agent can break that bond, and then the protein will end up being separated into whatever its subunit components were. Okay, so we've got our sample with our denatured linear proteins with their negative charge on them thanks to that SDS. Now we just need to run them on a gel. So this next part I'm going to be showing you what happens at a molecular level inside the gel and inside the tank. And instead of using the lab setup, I'm going to use this. Hey, still got it. Now in a lab we'd usually be running the gel between two glass plates and vertically, but here in the name of logistics I'm going to be running it horizontally in this thing. So the gel is going to be poured into a space that can hold a liquid to start with, and we've got this guy here. Here's the comb. It's going to sit in our gel chamber when we end up pouring our liquid gel. So here we've got the polyacrylamide. It starts off as a liquid, and when I pour it in, it's going to start setting like a jelly, and it'll set around that comb. So the comb, when you take it out, it'll end up having made these little pockets or wells, and we're going to pipette our sample with our proteins into one of those wells. But those proteins are so light that when you pipette them in, they're just going to float right out. So we need to add something heavy to increase the density of this sample with the proteins in it. We add glycerol, And when we do this, the proteins then will just sink and stay for the moment in the well, which is where we want them. Okay, so we've got our gel, and now we're going to hook it up to this electrophoresis unit. Now here up the top you'll see the negative electrode. It's called the cathode. That's because this is an electrolytic cell, which is basically a different kind of unit to a battery, where the cathode is the positive electrode. So here the cathode is the negative electrode, the anode is the positive electrode, and into this gel I'm going to load my proteins into that well. And if I were in a lab, this step would be done via a pipette. Okay, so I've got those proteins inside the well of the gel. Now when I apply that electrical field, whoa, check it out, the proteins actually move through the gel. They all have a negative charge, so they're getting pulled towards that positive electrode. And see, the small proteins are going to be moving fastest because it's easier for them to migrate through the gel. So the proteins in our sample are going to separate according to what size or what mass they are. Now this means if we take a sample, a different sample of proteins that have masses that we know what they are, and just imagine here that I've run this sample through the other well in the gel at the same time as the sample with our proteins of unknown size. Now we've got a standard, we've got a reference lane, and we call this the marker. So we've loaded these proteins of known sizes, they've migrated at the same time as our proteins of unknown sizes. And I'll just bring your attention here to the KDA that's up there. It refers to kilodaltons, which is just a unit of measurement, right? It's just how heavy they are. It'd be like grams or teaspoons. So we've got a reference for the molecular weight of our proteins, and you'll see that 250 kilodalton protein, or the heaviest protein in the marker lane, is the one closest to the negative electrode. The smallest, lightest protein at 20 kilodaltons has migrated the fastest and is down the bottom near the positive electrode. So we can make an estimate of the sizes of the proteins in our sample just by looking at where they are on the gel relative to where those proteins are in that standard reference or the marker lane. You see here that 200 kilodalton protein up there in red. I just put that because it's about between the 150 and the 250 kilodalton marker proteins. It's an estimate. So at this point I just want to give props to potentially the most useful symbol that I know. It's the tilde symbol, which means approximately. So when we make these estimations, we use this to say it's about or it's approximately 200 kilodaltons. Whoa, hey, time out, time out. These gels are like this big. The proteins that are in there are millions of times too small for me to see with my naked eye. So I've got to do something to the gel for me to be able to see the proteins that are in there. Now, on top of being very small, the proteins also have no color. So firstly, I add this Coomassie blue stain, which will bind to the proteins and make them appear blue. So once we've stained our gel with Coomassie blue, it'll come out looking something like this. We'll be able to see the protein bands on there. They'll all be blue. And just as a size reference here, I just wanted to show you next to that study mate ladder. Study mate? I will, mate. I will. What do you think we're doing here? And that's just there to show you that the whole gel itself is going to be something like 10 centimeters big. Each one of those bands doesn't represent one protein. If we had a magic magnifying glass and we could see inside, you'd see in fact each band there represents thousands to billions of copies of the proteins. And within each one of those bands you would see there are many copies of that protein, and all of those copies have migrated to about the same spot depending on what their molecular weight is. Okay, so just to sum up, in sodium dodecyl sulfate polyacrylamide gel electrophoresis, or SDS-PAGE, the denaturing gels, we first treated our samples with heat and SDS, a detergent, to denature, linearize the proteins inside. And that SDS as well, it imparted a negative charge to all of those proteins. Now, we could also add a reducing agent, which would go and break any disulfide bonds that might be in there in those proteins. And once we have our sample denatured, we then put it in the well of a polyacrylamide gel. And because all of those proteins are now negatively charged, thanks to the SDS, they're all going to move down towards that positive electrode. And those smaller proteins, they will travel the fastest and the furthest. So they will migrate depending on their size. So we use this technique to separate proteins out according to their molecular weight, their size. Okay, so the next kind of gel we'll talk about are the native or non-denaturing gels. Now for these gels, when we take our proteins, we don't add heat or SDS. So our proteins will keep these bonds that they have within them, and that means that they'll keep their charge, the negative or the positive that's on them, and they'll keep their shape. Now that part about the charge, whether that protein is positive or negatively charged, depends in part on its isoelectric point or its pi. Now that pi is a fixed number for each protein, and what it means, if you've got a protein with a pi of 9, if it's in a solution of pH 9, it'll have a net neutral charge. So if we've got a tube where all of our proteins are in the same tube, we can decide the pH of the solution inside that tube, and I'm going to add a buffer that's a pH of 7. Now, those proteins that have a pi that's higher than that pH, they will have a net positive charge. The protein here that's got a pi that's lower than that pH, it'll have a net negative charge. So it's both the pi of the protein and the pH of the solution that it's in is going to determine the charge, the plus or minus, on that protein. And if you want to hear a catchy little number that helps remind you of that relationship, please check out my video, the PI-pH song. Okay, so we've got our sample. Now we're going to get the gel together. Now in the native gel, we actually put the cone in the middle of the gel. So this means that when we pour the gel, the wells are going to form, here they are, in the middle of the gel. And I'll just say it doesn't actually matter which way around the positive and the negative electrodes are, because as you'll see, the proteins are going to move in either direction. Woo! So we get our sample, our proteins, and we'll put them into one of those middle wells. And you'll see now that they move when we apply that electrical charge. So we've got our positively charged proteins will move towards the negative electrode. Our negatively charged protein, that pink guy, he moves up towards the positive electrode. But also, check out those two positively charged proteins, the purple and the blue one down the bottom. They had the same charge, but that blue one, because he was a smaller protein, he still migrated faster through the gel towards that negative electrode. Okay, so to sum up the native or the non-denaturing gels, we don't denature our proteins before we do this. We leave them in their native shape so the bonds are intact, and also they have a charge on them, their own native charge. Now, what that charge is will depend on the isoelectric point of the protein, so it's pi, but also the pH of the solution that you put those proteins into. Now, when we run the gel, we put our sample into the middle well, so the wells are in the middle of our native gel. And then when we apply the electric field, those positive proteins will migrate towards the negative electrode, the negative proteins will migrate up towards the positive electrode, but also those small proteins will travel faster than the large proteins. So this is a way of separating proteins according to their charge and their size. Thank you so much for joining me through this. If you've got any questions or comments, please just put them down there in that comment section. If you thought it was all right, please give it a thumbs up. And I look forward to seeing you on the next The Awesome Biology Channel video. The Awesome Biology Channel. Please subscribe, please subscribe, please.